Hi there, my name is Georgia Stamper, and I will be explaining number 1 on the written homework number 3. So the question asks, show that f of xyz equals xyz over x squared plus y to the fourth plus z to the fourth approaches 0 as xyz approaches the point 0, 0, 0 along any line x equals at, y equals bt, and z equals ct. Does this imply the limit equals 0? If not, determine if the limit exists or not and prove your answer is correct. So how we're going to start this off today, I have my little handy dandy whiteboard here, and I have the problem written up. So what we're going to do is first we're going to analyze the lines x equals a of t, x equals at, y equals bt, and z equals ct. So if we think about a standard linear form of a line, we think y equals mx plus b, where b is the y-intercept. For the case of the lines that we have, all of our b's equals 0, which indicates that all of these lines go through the origin. Their y-intercept is 0, which is the origin is 0, 0. So we can determine that all of these lines approach 0 as x, y, and z approach 0 respectively. So now that that's out of the way, what we're going to do is we are going to substitute those lines in for their respective variables in our equation that we're analyzing today. So we have f of x, y, z equals a of t, which is equal to x, b of t, which is equal to y, and c of t, which is equal to z, all over at quantity squared plus bt quantity to the fourth plus ct quantity to the fourth. So that's what that looks like right there. So what we're going to do with this is I'm just going to manipulate it a little bit. So I'm going to factor out the t's on the top, and I'm going to distribute the exponents on the bottom and see what that gives us. So that gives us a, b, c, t cubed on the top, and on the bottom we have a squared, t squared, plus b to the fourth, t to the fourth, plus c to the fourth, t to the fourth. So what we can do from here is we can factor out a t squared on the bottom of the equation, which I'm going to do. So you have abc t cubed over a squared plus b to the fourth t squared plus c to the fourth t squared all times t squared. So we just took out a t squared and that left the a squared by itself on the bottom. So what we can do with that, here, let me show you. So these are our steps that we're following. So what you can do with that from there is that you can simplify that you have a t cubed over t squared, and you can simplify that so the t squared on the bottom goes away that you factored out, and the t cubed on the top becomes just a t. So now we have abct over a squared plus b to the fourth t squared plus c to the fourth t squared. So how we determine if this function approaches 0 as the point xyz approaches 0, we can take the limit as t approaches 0 because t is the parameter of all the lines that we were given that were equal to our variables in the first place. So what we're going to do, so we're going to take the limit as t approaches 0 of a, b, c, t over a squared plus b to the fourth t squared plus c to the fourth t squared. So here's just a visual of that real quick. This is our limit that we're taking. And so if you take that limit and you plug in 0 for all your t, you have left 0 over a squared, which equals 0. So the limit does equal 0 as t approaches 0 of this particular case. But to determine that a limit exists everywhere at 0 means that you have to test every single point. So in order to determine if this limit does not exist, we have to find a counterexample, which is what I will show you in the next part. Alright, so we found out that the limit as t approaches 0 equals 0, but that does not necessarily, from the specific lines x equals at, y equals bt, and z equals ct, but that doesn't necessarily mean that the limit itself does equal 0, because for a limit to exist, it has to exist at the same point everywhere. So in order to determine that this is not true, we must find a counterexample. So as we've kind of come to determine, basically any line is going to give us a limit of 0. So, but since we're in R3, we can use any curve as the line that we're coming into 0, 0, 0 from. So I've decided to use the curve x equals y squared and z equals y. So therefore we can rewrite our function f of x, y, z as y squared times y over y squared quantity squared plus y to the fourth plus y to the fourth. So we can see that here we are just plugging in this curve into this function to get here. That's where we are. So to determine this limit, you're going to take the limit. So I'm going to take the limit as x, y, z approaches the point 0, 0, 0 of, and to condense this down, we have y to the fourth over 3y to the fourth. And if you were to just take the limit of that, that gives you, or not even if you were to condense that down, you have the limit of x, y, z approaches 0, 0, 0 of 1/3, because the y over fourths cancel, and that just gives you 1/3. So to give you a visual of that, here we are. We came up here and we took the limit and we simplified the y to the fourth. And since we found a curve where the limit does not equal 0, 1/3 does not equal 0, this in turn means that the limit does not exist. And